Electrochem, last time we talked, I know I spent way too long talking about alternative energy. It's the big challenge of not your life so much, but your children's lives. They will, towards the end of my life, I will see Hubbard's Peak. I will see the beginning of Hubbard's Peak, and I'll be glad to go out by then. You folks will see some pretty bad things happen. You're going to see gas prices just explode. Your power bills are going to skyrocket. Your kids are going to grow up in that world, and it will be a very different one. Batteries are, we are pretty sure batteries are a big part. Solar is what we think is going to be the solution. There's some idea about nuclear. We talked about that. One of you asked me about ethanol. Actually, what's happening is we're already farming most of the land we can farm. So ethanol would be a form of solar energy. Grow corn, turn it to ethanol, burn that. For one, it doesn't actually solve the sky turning black or CO2. That's not a good solution. The second thing is there's not enough land. Wind, there's actually areas of the earth that have strong enough wind to give us good power that can increase our power generation by 5%. 5% of what we need. Basically, it's not a solution. Nuclear we talked about. There's the idea of the tokamak, which is fusion. Right now, no one thinks it's actually going to work, and that sucks. That would be a game changer. But again, right now, we don't think it's going to work. So solar seems to be the only reasonable thing. It's just that at night, we're going to have to use batteries. Batteries are not really very efficient. Right now, it's a problem. If any of you go into battery research and can make a battery more efficient by 1%, you would be wealthy. That's a very big deal. Whenever someone comes up with a solar cell or a battery that's 1% more efficient than the last generation, they get like Science and Nature articles, which you've probably heard of. That's like a really big deal. 1%, here's my point, 1% is a big deal. 1% greater efficiency in a solar cell or a battery is earth-shattering news, and whoever comes up with it is rich. So you might want to go to grad school. All right, now last time we talked about how you're going to get the number of electrons and you get their charge, which is just a constant that relates number to charge, coulombs per mole. That's Faraday's constant. Here's a hint. Don't memorize this. I'm going to focus more on test-taking skills from now on in these lectures. Here's a hint. Don't worry about remembering F. You're not going to need it. And don't try to remember you don't need it either. All right? Now you've got to translate coulombs to delta G. And notice I didn't put a little circle there either. All right, that's coming up. Okay, so E is your translator. That's voltage, which you now know has units of joules per coulomb. Now, for historical reasons, there's a minus sign. And that just means, well, for one, it means that Ben Franklin thought electrons were positive, and that has been a problem that has infected all electrical engineering and this class to date. Number two, it means that everything we calculate is actually going to be backward. I'll get you just used to that by example after example. Okay, now, this thing, you know what this is. This is the Hess's law. Bit plus RT. I need to be doing this per mole. I need to be doing this per mole because I didn't write N. Now, I'm going to use the letter Q because you are not at equilibrium. Okay, now remember this is going to be, you can make batteries that run on gases. I will show you a few examples. Hydrogen, right? You might have heard of the standard hydrogen electrode in freshman chem. I will go over it. You can build batteries out of gases. In fact, that's thought to be the generation of batteries that will allow planes to fly. And think about this. We're running out of oil. That means no kerosene. Kerosene is jet fuel. How do jets fly? You're going to get on a jet that runs on batteries? Really? Yeah, that's scary, isn't it? A jet that runs on solar power? How in God's name would that work? It won't, by the way. But there is a thought that you could build what's called a lithium air battery that has the power of basically a gas engine. Now that means that big 747 Streamliners, no, we're not going to fly those anymore. But if we can build lithium air batteries, then we could have decently big planes that could fit like 50 people. So we might still have that 50 years from now. Anyway, the point about air is that I showed you how to do equilibrium constants for gases, so that still works just if the battery's made of gases. I'll show you how that works in a minute. So again, this is your products over reactants. You can think of it as partial pressures for our gas battery of reactants over products over reactants. Sorry. The difference is they're not at equilibrium. Okay, a battery at equilibrium. How good a battery is that? You don't want to talk to me right now, do you? It's a very bad battery. A battery at equilibrium is a dead battery. And if I ask it on a test, right, test-taking skills, the way you would know it is a system comes to equilibrium if you wait long enough, right? So don't memorize this, just think. Everything comes to equilibrium if you wait long enough. If you wait long enough for a battery to come to equilibrium, you know that it's a dead battery. All right, so we do not study any of this jazz at equilibrium because nothing works anymore. Batteries are inherently designed to work not at equilibrium. So that's why we use a different letter here. But spoilers, we're actually just going to ignore this because a lot of materials in a battery are solids, and that means that the reaction quotient actually doesn't really change too much till the battery is dead. There's a couple other reasons. I'm going to cover that in a minute, but for spoilers, we're going to actually ignore this because it's just not that big a deal. Anyway, okay, so being OCD, I'll write this down. Okay, so now when it comes to batteries, I don't actually care too much about this. I mean, we've been focusing on this. But when it comes to batteries, I don't really care about that. I care more about this. That's the voltage. Obviously, the voltage of a battery is really freaking important. Kind of. That's actually not so true, but this is how I want to introduce you to this, is cover voltage. Really, a battery current is kind of more important. Current is power. I squared R. Maybe some of you remember I was trying to learn electronics in high school, and I know that that's the power that you generate. And that's kind of more important, especially if you're going to build a lithium-air battery and fly an airplane on it, which is the idea. The only way we'll be able to do that. Okay, so anyway, and I'll tell you a little bit how you design current. We're going to talk about that today as well. For now, I'm going to focus on voltage. Just in your own future, when you get out of here, remember that current is actually technically more important. Also, here's another little factoid about voltage. It doesn't kill you. When you think about getting electrocuted, voltage doesn't kill you, current does. When you get zapped by a doorknob, especially in winter coming, it's 10,000 volts. It kind of stings, it didn't kill you. If the current is a milliamp, you're dead. All right, but the current is a milliamp because there's not enough electrons. Okay, so we focus on voltage, so I'm going to solve this sucker. I'm going to solve this sucker for the voltage. And this is voltage, by the way, just like you know it. The 9-volt battery, this is the 9. Right? So anyway, a little algebra. Whichever equation you need will be on the cheat sheet. There you go. So this is the voltage. Okay, now here's a little factoid that's actually terribly important. And don't worry about it so much now, but I'm going to show you here in a second. We call this little thing right here, this gets a special term. You know, I don't like memorizing this kind of stuff, but in this case it's actually hugely important. This is called the standard EMF. That's electromotive force. I'm not going to write it down because I'm not going to test you on that, because you know I don't care too much for words, and I'll let you know when I do. Okay, so this is the standard EMF. Now, the reason that this sucker is important is that we're gonna solve the voltage of batteries via Hess's law. That works because I can relate voltage to delta G. Delta G is energy. Energy is added by Hess's law. So what I can do is analyze a potential battery. I can analyze it in delta G, figure out how the reaction goes downhill, and then translate that back to a voltage. Now, the thermo data, the Hess's law data, the table in the back of the book, is no longer going to be forming chemicals from elements in their standard state, because that doesn't make sense. It's actually going to be in the form of standard EMFs. It's just an example of how you can analyze anything energetically as long as you pick a consistent reference state, which is remarkable, right? Because now remember, I could figure out the G of electrons. I can figure out the G of ions and solution. I can figure out the G of anything, not the delta G, the G. I can do that, but it would cost a lot of money. Instead, I make an easy measurement from a reference state, and as long as I always use that reference state, anything else I do is fine, and it will work and will be accurate. And the reason I do that is that the reference state is much easier to, it's an easy reference state and the measurement's easy. Okay, anyway, you'll see in a second. So this is our Hess's Law table at the back of the book, so that's why that's important. Okay, just so you get a little bit more about how this works, let's say that you have a reaction, and I'm forgetting the per mole, sorry about that. Let's say that this is the delta G per mole. What is E naught in this case? And let's say that it's a one electron reaction, like, you think that most reactions are one electron reactions. It's not really true, but anyway. Okay, let me solve E0, and then let me just comment on that. Okay, so this is minus. Okay, so this might be somewhere I can try to screw you up, is you got to remember your standard SI. Kilojoule is not standard SI, and I forgot per mole. Okay, minus, so this is going to be plus. Here's the number of electrons. That's why I needed to provide that information. Here's what Faraday's constant is, which I don't think you will see again, and you'll understand why in a minute. That's why I told you not to worry about this so much. The units are coulombs per mole, right? And so this ends up being joule per mole, which is a volt, and this is approximately 1 volt. 1 volt. Okay. Anyway, it gives you a feeling for scale, but probably not. Now, for me, this works because I'm twice your age, and this is what I do for a living. This doesn't sound like a lot. But let me tell you this, if I was in a lab and someone said they had a round bottom, they were about to set off a reaction that was negative 100 kilojoules per mole, I would back away. Why? Any opinion? Because that's explosive. This is the delta G of most explosive reactions. That is a gigantic number. It's a terrifyingly large number. Now, remember I told you yesterday, I would tell you why Dreamliners were catching on fire. Because a battery that can produce a volt has a very powerful chemical reaction going on inside of it. And actually, and I'm going to show you a little bit more in a minute, I'm just going to go ahead and do spoilers. Chemicals that react violently need to be kept apart. But the way a battery works is that those chemicals are kept apart by a very, very thin, like 100 micron. That's the limit of that's the size of a hair. That's the limit of your eye's ability to see. Those chemicals that will explosively react, and that's how you only get a volt, are held apart by the width of a hair. It has to work that way, and I'll explain that in a minute. If something goes wrong and those chemicals touch, it's no different than gas and flame oxygen. Right? That's about the same delta G. Actually, that's about minus 800. But anyway, you get the point. That's why those things blew up. 1 volt is actually pretty freaking powerful. All right, so what am I going to actually do is all of this voltage stuff comes down to Hess's Law and understanding, Hess's Law. So there's some conventions I'm going to go over, and then I'm going to have an emphasis on question answering for obvious reasons. There's some terminology you need to know, but I will not hold your hand. I'm not going to hold your feet to the fire on this because I don't care about just remembering words. What I do care about, hint, hint, Hess's Law, and I'm going to be very clear about what I think you should know for the third exam, perhaps the final. Okay, so something, I have trouble keeping this straight. I've gotten better at it, again, because I do this for a living. I know when I was your age, I really could not keep this straight. Is you have to keep, now again, for my purposes, I'm not going to go nuts if you can't quite remember this. Okay, this is all about electrons and addition of an electron is reduction. Likewise, the loss of an electron is oxidation. Okay, again, I don't see myself testing you on this, but there it is. Maybe some of you will go to grad school and study batteries. That's something that's actually kind of explosively taking off for all the reasons I mentioned yesterday. You would need to know that. The rest of you not so much, and that's fine. One thing I want to point out, though, that slays me, even though I do this for a living, and this kills me. This is why I have trouble remembering this. This word has 5 or 6 different meanings. That's unfortunate that we do that in chemistry. Actually, every field has jargon, right? Words that are only applicable to that field that are designed to keep other people out. Right, so in chemistry, we tend to have, like I say, I swear to God, at least 5 definitions with the same word. Oxidation, I would normally say, means a reaction with oxygen, and that's correct. When things oxidize, they tend to lose electrons, right? So that's why we borrow the word. It also confuses people, and when I was your age, I often got confused. That's why I'm not going to hold your feet to the fire on this. If you do feel like you want to remember this, remember that I have a little mnemonic. Gaining negativity reduces you. Okay, just a little mnemonic like the energy bank. It's positive to store energy, right? So there's one for you. You saw what I did on the last test with 80 beta irreversible, and I'll talk a lot about that on Friday. Yeah, anyway, there you go. So in terms of like why even a 1-volt battery is dangerous, let me go ahead and design a battery. And this, I think, again, I don't see myself putting this on a test because there's not really a lot to say about it, but it is kind of fascinating how battery design works, especially in the light of how some batteries were catching on fire and how powerful these reactions actually are. I mean, again, when I was your age, I never really thought about that. I never considered a battery dangerous. Samsung's catching on fire, green lighters burning in the sky. They actually are, and I just showed you that. So let me show you a little bit why about how you engineer these and why, yeah, they're kind of nutty. Then again, you're driving around in a car with a gas tank full of explosives. You can't really avoid that. You just gotta have to trust engineers to have done a really, really good job such that this stuff is safe. But I can't emphasize this enough. A lot of your typical devices, your cell phones, actually do have surprisingly powerful chemical reactions inside of them. And yeah, anyway. Okay, so here is a beaker with a liquid. The liquid is salty, probably full of sulfuric acid. We'll go over that in a minute. And I have 2 metal electrodes. All right, again, we're designing a battery. We're figuring out which way the electrons go. We're figuring out which way what the voltage is. That's the point. And I'm going to put a little voltmeter. And I'm going to see the electrons travel. If they didn't want to do that, I would measure 0 voltage. So here's a little funny thing about voltmeters. Probably some of you gearheads were kind of obsessed with these as middle school students, high school students. When you have a working voltmeter, actually does not allow electrons to travel between the 2 electrodes. That's a short circuit. You don't want it to do that. What it does is actually it's measuring delta G. That's kind of my point. It's measuring the delta G for electrons to go, but it doesn't let them do it. And that's called an open circuit voltage. That's actually one of the most important characteristics of a solar cell, an open circuit voltage. You might hear that sometime. Even in like New York Times, when they write about solar cells, they mention that that's a big issue. So when you measure current, you actually do let it flow. And that's why when you have these meters, that's why you have to have different settings for that, because the machine, the insides have to be prepared to allow current to flow. Otherwise, the damn thing gets fried. Anyway, blah, 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 not a big deal. All right, now let's say that we have, gotta remember this. Let's say we have zinc and copper. Zinc and copper. Okay. Now, in this case, the electrons are going to flow from zinc to copper, and this is the chemical reaction that occurs. It is very important to keep it straight what is aqueous and what is solid. Now, again, I won't test you on that because I don't really need to. I'm going to, in just one moment here, I just need to get through some of this stuff and I'll show you exactly what I expect folks to figure out from these things. But anyway, all right. Primitive battery, salt solution, 2 electrodes, voltmeter, and what I'm seeing is zinc and copper. The zinc is delivering electrons to the copper through the electrodes. That's what I'm learning. And the reason I know that is because zinc is dissolving. And copper is plating. Okay, so again, I built this sucker. My zinc electrode is dissolving. My copper is getting bigger. I know that this is happening because it's kind of obvious. I'm forming solid copper. I'm losing solid zinc. I know that that's happening. So it's not too hard to figure out where the electrons are going. And you can see that I can tie the two together via Hess's law. Right? I just need the copper. I need to cancel out the electrons. Again, that's important. You need to cancel out the electrons. And I'm going to work you on that several times, give you lots of example problems. Okay, so again, I'm just doing the Hess's law bit, which will be half credit on the questions that I asked on this, just doing this much. Of course, that's not going to be enough to pass, but anyway, all right, so there's the Hess's law result. Okay, now again, what I'm going to mostly focus on is I've given you this information, but no more. From now on, I'm going to have you figure out. I'm going to tell you that there's zinc or copper or aluminum or hydrogen gas. I'm going to show you gases. I'm going to just tell you what the battery is composed of, and you're going to tell me what happens. I'm going to show you how to figure that out. All right, before I do that, and that's what I'm going to spend the rest of the time on, I want to go over battery design, because this is like the big thing that scientists are doing now, and it's really important. Okay, again, this obviously needs to be a salty solution. Even if it wasn't salty, it's becoming salty because of that. Obviously, there's a counter ion, there's anions present, it's probably sulfate, sulfuric acid, just like in acid batteries, right? Okay, but now my point here is this is a terrible battery. That is the world's worst design of a battery ever. Guess why? Can you guess?
It's doing no work.
What is the worst thing you can do to an electrical circuit?
Equilibrium.
Well, of course it's going to equilibrium, but it's not there yet. I have acid and I jam 2 electrodes into it, into salt water.
Because the solid will come and accumulate in the middle.
Well, okay, so the word I'm looking for begins with an S. What do all circuits do when they fry? They short circuit. So you're all saying the same. Yes, because it's short circuits. That's correct. Everything you said is correct. Because it's short circuiting. The electrons are just going to go through the water. Right? That's stupid. I can add a load here. That's the electrical terms for your watch or something, your iPhone. But it won't care because the electrons will just flow through here much easier. So, primitive first step is to add a barrier. Add a barrier such that the electrons just basically can't go through it. That's the idea. It's literally a physical barrier for the electrons, giving them simply no option but to go through the load. If no load, and again, load is your iPhone, right? If no load is present, nothing happens, the battery is preserved. Of course, over time it won't be, but the reason that is that, here's the number 2 thing. True and false, perhaps. This is a true and false question, by the way. If I set this up just like this, and again, a physical barrier, this is going to work for about 1 second. And that's because when I add a load, the electrons go from this side to that side, building up a negative charge here and a positive charge there. It will take very little time for the delta G for electrons from flow from right to left to be counteracted by the charge that pushes them back. So remember, because of the delta G, electrons want to go from here to here, but the electrons see a negative charge, and they're attracted backward to the positive charge that remains. That pulls them back. Keeps them from going forward, pulls them back. Eventually, really quick, the charge stops. So you can't have a physical barrier like a piece of, I guess metal would be bad, a piece of plastic. What you have is a piece of plastic that would allow ions, like negative ions, to go this way, and positive ions to go that way. It's a semi-permeable membrane. That's the idea. So when the electrons do what they do because delta G requires them, what this allows is for the electrolyte to respond in kind such that the electrons keep flowing. That's the idea. It's kind of like a dumb mistake. Without this ability for ions to diffuse, you run into a dumb problem, which is the buildup of charge, but it's a dumb problem, but it's a serious one. Okay, now we run into another dumb problem. We have all kinds of semi-permeable membranes. You are a semi-permeable membrane. Your cells, your phospholipids that make your cells are good about transporting charges of one type or another. All right, but, it turns out that all types of membranes that we've built generally only work for either cations or anions and not both. Right, so you would halfway solve a problem. So again, put any material that you can ever think, find, make, synthesize, whatever, put any membrane, right, other than a big solid piece of plastic, I already said that doesn't work. Pick any membrane, one of the ions will flow and the other not so much. Doesn't work. Now remember, I also said current matters. Right? Current is more important because that's where power comes from. You see what actually limits your current? Is this has got to happen. You think electrons are moving quickly, and you're right, they do. But they only move because these ions move too. So here's one of the biggest secrets about battery design. Ions have got to move efficiently, or you run into that problem I just mentioned. So when you design a battery, you can't just assume that it's going to deliver current like mad. You know, you hook it up to, you have a big battery, you hook it up to your Tesla engine, and current flows like crazy. It depends on the ability of ions to diffuse inside of it to prevent that dumb problem. That's how that is the number one problem in battery design right now. Isn't so much generating the voltage or knowing what reactions work, it's getting the ions to move, because that's the part that actually limits your current. Current is power, and power is everything, right? Okay, so the way we figured out how to beat that problem is, and this is literally 1800s. So another reason I like to cover this is, again, because of world power problems, but also because it does show you, I think these problems are they're kind of interesting, just in their own right. I'll probably read about this even if I wasn't doing what I do, just because it's just how things work. Okay, so 1800s. Let me go back to 1800s, and I'll talk a little bit more about actual batteries. This is a Daniel cell, by the way. I won't break that down. What you do is you split the electrolyte into two. And this is a bit of a pain to draw. Fortunately, I had lots of practice since I've done this 15 times or so. Okay, you've got your two electrodes. So you might want to label that. These are your electrodes. And I know you actually had this in freshman chemistry. Hopefully you know what I'm drawing. Is a salt bridge. Okay, and then here's your zinc. Here's your copper. Again, it's still got acid, and the salt bridge is usually a gel type of thing, and that's just so that it can be filled. So I'll try to make that clear. There we go. So it's still clear, and you've got your load, which I'll put in the form of a voltmeter, and the electrons are still going to go this way. Yada yada yada. Okay, salt bridge. again, an engineering aspect. It allows ions to flow, but essentially there's two things about it. One is you just actually, you got the two metal bars like much further away. And the current is not going to be able to go through the solution nearly as well. Right now, the ions are going to diffuse like mad. They've got no problem diffusing between left and right and left. That's very easy. But the electrons, not so much, because the distance between the two bars is now much, much further. And it's just a matter of resistance. Actually, when I was in high school, we had to measure the resistance of metals, and the way we did it was we had a strip, we had two electrodes, and the figure of merit is how resistance changes as you push the two electrodes away from each other. That is how you quantify materials in terms of their conductivity, is how much charge you get as you push these two electrodes apart. It just makes sense, right? So another thing that happens is, gotta have to get this right. Okay, so you're actually going to build up negative charge here, and that still happens, but due to the fact that there's an interface, you're actually going to end up doing this. It actually builds up a set, and don't memorize this, maybe don't even write it down. It's another little practical engineering effect. You end up building these, there's actually a word for this, I'm forgetting it, that polarization. You build polarization at the interfaces, and that actually, again, is something that impedes electrons from flowing through the salt bridge. So electrons like this, but they don't like that. If they get through, they like this, but they don't like that. And there's a large distance, electrons just don't flow. They do, but very, very slowly. That's why batteries die. You add a load, they flow like mad, right? And that's why these things work. So the other thing I wanted to tell you, and then I'll give you your test back and you can murder me online, is, it's all right, I can take it. All right, so you see now what the biggest part of battery design is actually connecting these two suckers here without getting an explosion, because modern batteries, like lithium-ion batteries, what you have here and here is an explosively powerful reaction with just like a little membrane, as I showed before, a little membrane that barely keeps them apart. Keeps them apart such that you get current to flow where you want it to flow, but still keeps them close enough so that the ions can diffuse quickly, and that's what gives you your current. And those are two diametrically opposed problems. You need a barrier, again, so that electrons flow the right way, but it needs to be thin so that the current is very high. The problem is, if it's too thin, Dreamliners catch on fire, Samsungs blow up. Right, so that's really a major problem.